Behind every stunning 3D scene and every smooth animation in games lies a mix of math and creativity working together to bring objects to life. In this video, we'll explore our project titled 3D Computer Setup with Graphic Transformations. This project demonstrates how concepts from linear algebra like rotation, scaling, reflection, and translation can transform 3D objects in a virtual space. Using HTML for the structure and JavaScript with the Three.js library, we built a 3D computer setup that showcases how these mathematical transformations control movement. Let's begin by explaining our HTML file, which serves as the structure of our project. From line 1 and 2, it declares the document as HTML5 and specifies English as the language. The head sections, or the meta tags, make the site mobile-friendly and correctly display characters. The title in line 6 appears in the browser tab when the code is totally running. Now, let's take a look at how we coded our index HTML file. We started by setting up the overall look of the web page to make it clean and full screen. CSS removes all default margins and hides scroll bars, so our 3D scene fills the entire browser window. Chose a soft light blue background and a simple Arial font to keep everything neat and readable. Next, we styled the title, positioning it at the top center with bold text and a subtle shadow so it stands out clearly on screen. Finally, we placed the control buttons vertically on the right side of the page, making them easy to access while we apply transformations like rotation, scaling, and resetting the 3D model. Now, let's move on to the JavaScript section of our project, which is responsible for creating and animating our 3D model. A new 3D scene object is then created. This scene acts as the main 3D environment where all objects, lights, and cameras will be placed. The scene background property is set to a light blue color to give the scene a soft and realistic background tone instead of a plain black screen. Now that we have finished setting up the scene, camera, and lighting, the next part focuses on building the actual 3D objects. The parameters A, 0.3, and 3.5 define the x-axis, y-axis, and z-axis of the table. This corresponds to the basis vectors of 3D space scaled by these values. In this part, we are creating the monitor for our 3D scene. We group all its parts, the frame, screen, stand, and base, into one object using tree.group so we can move it as a single unit. The frame and screen are made with box shapes, where the frame acts as the border and the screen sits slightly inside it. Then we add the stand and base to hold the monitor upright and make it look stable. Each part has width, height, and depth values that keep it centered and balanced. After that, we combine all parts into one group and position the whole monitor at the center of the scene, ready for rendering. This is where we move the entire monitor group down in the scene. This code creates a 3D keyboard model made of 4 rows and 12 columns of keys, positioning each key using linear algebra through vector addition and scalar multiplication. The code creates and positions the mouse and CPU objects in a 3D scene, scaling, moving, and shaping them properly to fit the setup, with the mouse slightly right and forward, and the CPU group with its parts like the power button and drive slots. This is our original 3D computer setup before any transformations. At this stage, our 3D model is still in its default state. As we can see, our computer setup is now rotating. When we rotate, we are turning the object around the y-axis, meaning it spins left and right. That 0.02 number might look small, but it's actually in regions, not degrees. So, in each frame, the object rotates by 1.15. That's why it looks smooth and slow, not sudden or glitchy. Now, we can see that our 3D computer setup is now scaling. Scaling means making the model bigger or smaller, but keeping its shape. Here, at the code, we can see the scale factor starts at 1, or the normal size. Each time we run the function, we add 0.1 so it grows gradually. When scale factor is equals to 1.5, the object becomes 1.5 times larger in every direction. The last linear transformations that we have is the reflections. Only the mouse and CPU tower have reflections so that the changes can be clearly seen. If all objects were reflected, it would be harder to notice the difference. This line multiplies the x-axis scale by -1. Multiplying a negative number doesn't just resize, it flips the object. This is the reflection matrix, so the new coordinates become it flips across the YZ plane. That's the plane where x is equals to 0. In conclusion, our project demonstrates how mathematics and programming work together to create three-dimensional visualizations. Through the use of linear transformations, we showed how matrix operations can manipulate objects in a 3D space. It shows how linear algebra serves as the foundation of computer graphics and animation. The project was proudly created by Francine R. Robot and the Yesari Bulbos, showcasing our collaboration in connecting mathematical concepts with real-world application